Okay, in this last video, we're going to cover trend adjusted exponential smoothing. It's an advanced method. It actually combines exponential smoothing and trend. It combines exponential smoothing and trend. It's called double smoothing because we have two smoothing constants. Obviously, this can be extended to triple smoothing. I think that's called Holt's method or Winter's method. Winter's method, yes. It's a triple smoothing technique. But it's a little bit more advanced, so I'm going to show you how to do it. It's not in the book, and I'm also going to use Solver to optimize my initial conditions as well as my smoothing constants. So back to this problem. This was our houses sold, and for trend adjusted exponential smoothing, this is going to be my forecast, but it's going to be composed of this S and this T, and these are the formulas that I'm using. So S is kind of like the original exponential smoothing. And how you calculate it, how you calculate S, is you take the forecast, the TAF, on the same time period. So when you see the in parentheses T, that's the same row. It's the same time index. So for the second time period, if I'm trying to calculate S, I grab the forecast for that plus alpha multiplied by, in parentheses, that current row's actual minus the difference, minus the forecast on that same row. And then to calculate the trend, which is now it's just like the slope, how the slope can be adjustable, I take the previous slope plus beta multiplied by TAF minus 1 of the previous time period minus the previous slope. And then TAF is equal to the previous time period's S plus T. So I can copy these down, all of these down, all the way. And in addition to that, so this is the future, so I don't need any of these. That's actually the forecast into the future, but I'm not going to worry about those. Now I'm going to calculate my absolute percent error, and that is the difference between my forecast and what really happened divided by what really happened. Show it as a percent, copy that down, and then my MAPE is the average of all my absolute percent errors. So this is it. The red, so you can see as I change these smoothing constants, these numbers change. These forecasts, the red changes. Now the trick is I want to make these numbers, set those to make that as small as possible. But the other thing is I need to have some initial conditions like these. And all I'm going to do now is I'm actually going, in my optimization, I'm going to let the model control these as well as these. So 4 variables, because these are my initial conditions, these are my smoothing constants, make that as small as possible. These have to be less than or equal to 1. So now when I go under Solver, I want to minimize this value by changing these two and these two. And I'm holding the control key down to grab data that's not connected. Then I'm going to add that these have to be less than or equal to 1. This is nonlinear. The MAPE formula uses the absolute and it divides by things, so it's a nonlinear function. But that should work. So now when I hit solve, there you go. So it says what we should set our smoothing constants are 0.84 for alpha, 0.03 for beta. The initial conditions that work best is to set S equal to 221 for the first time period, and the trend set at 0. If you notice what in previous videos when we used exponential smoothing, we were getting 5.06, so we were able to improve our MAPE using trend adjusted, not by a lot, but it is better, and we've got a more accurate, or a forecast that's more dynamic. when this slope changes, it was able to transition to this quicker, and since this is a slope, it's done a pretty good job. And even then, it captured this, which is pretty cool. Okay, that's an advanced method. What I mean by advanced is that I'm not going to test you on it or any homework on this one. Thanks.